Good evening, everyone. I am very honored tonight to present the last of the lecture series before going to Geneva. It's an honor for me to introduce Ariel Schlesinger and David Stojevic tonight. Ariel Schlesinger is an artist who graduated from Jerusalem Fine Art School in 2003. And from that moment, he had like a professional career that spanned throughout all over Europe, in France, in Germany, in Italy, and in UK as well. And his main focus is the attempt to deconstruct conventional processes of manufacturing and conceiving object-related processes in what he calls the reverse engineering that he will explain later on tonight. And Vid Stojevic is a scientist, is researching into the field of string theory. He graduated from Imperial College and is currently developing his studies and his research in King's College in London. And it's a great honor to have them here tonight, and please welcome them. Thank you very much.
Hey, thanks all for coming. It's strange to hear myself. I actually thought to start with a really something. I hope it's going to work, but does anybody ever used one of these? Yeah, it's fun. Okay, maybe we just come back to it later. Okay. Yeah, nothing always. Oh, okay. Train hopping and reverse engineering. So I chose these subjects just as a kind of introduction to my work. So I'm not really going to go really deep into them or in a very technical way. It's more going to be a way how I experience these things during my adolescence and until now. Train hopping. It's actually still happening all around. Mainly, I think, in North America. That's where I first encountered it. And in Europe as well. And these days, the people that do it are, I think, mostly either punks, that for them it's a really easy way to travel without needing the help of hitchhiking, which is probably really hard in America. Ex-vets, so people that were drunk people, alcoholic, that for them it's a way of living, and they're just bumping in from town to town. And even yuppies that do it just because it's really cool and they have all the gears, and it's probably they invest more money than just catching a flight. And the principle of train hopping is really simple. This is the guy actually that exposed me to train hopping. So it's really a principle, a very, very simple idea. There is a vast train network of freight trains moving around stuff, starting from refrigerator to maple syrup to cars, garbage, whatever you would imagine. And these trains are just going constantly. So there's actually no lot of information on where they're heading, or there's no signs on them. And the idea is that you have to. I'm sorry. Sometimes I'm missing some words, but you would need to hide and wait for them and kind of catch them, like a predator. And usually you would hang up in areas that are full of garbage, really stinky, and you will just wait and be cold and hungry until you really think there is no chance you're going to move from this stinky point, and then suddenly a train coming, and you just know, like, okay, this is going to be my train, and in that moment, everything starts really fast, because the train just, this massive metal object just rolls in the middle of the night, and you have to of course, there's a lot of techniques how to do it, and how to jump, how to run, but the really basic idea is that you're kind of running in the tempo until you get to the tempo of the train, and in that point, you're shifting on it. Of course, there's different cars with different, they're not meant to be ridden, yeah? So there's no big signs, watch the gap, or you know, it's really just this constant movement that you have to go adjust yourself to. And then, boom, I mean, you're just on it. And in that moment, everything changes, because you're part of this massive metal thing that just have no any connection to you, or I mean, it doesn't mind if you're on it, not on it. If you're under it, it will just go on top of you and cut your legs, cut your arms. I mean, it's really dangerous, and it's moving, it's loud, it's dirty, it's cold. But being on the train is just like a huge, it's just something different. And it's really, in a way, very addictive, because I guess it's impossible. I mean, it's, yeah, okay, no, well, let's continue. Another beautiful thing about it, that once you're riding on the train, you're really passing through areas that you would never pass before as a traveler. I mean, if you would rent a car and drive around the United States, for example, you will always be surrounded by billboards, by McDonald's, by hotels. And in this case, you're just out in the wild. You're in this massive industrial cold thing, but it's actually really swimming through the field in just completely natural environment. The moments, the places that you can relax a bit usually look like this. These are kind of spots that you would find in either ends of grain cars, mainly cars that transport either cement or grains. And from some reason, there is some people believe that there might be a secret hobo. Hobos are, that's the term that people call themselves as train hoppers, hobos. So some hobos believe that there was maybe an inside job, because it's just a perfect place for you to kind of hide from the cold wind or hide from authorities. I mean, there's always a kind of chase between the police, the bulls, the train police, and you as a traveler. So there's a big extension of time where you're just out in the wild, but then you're, of course, you're gonna in some point pass through a yard, a train yard, for the crew to change, and then in these moments you have to immediately hide. You can really, people get really creative. Sometimes they crawl under the truck. Sometimes they even sneak into one of the engines, yeah, into the place where the train riders will be, just to find a safe spot. Yeah, so like I said before, there's probably as many hobos out there. There's probably as many techniques and stories and ways of how they do it. So really, it's something that is, yeah, whatever. Okay, jumping on. These are jerry cans. And the reason I was thinking about these jerry cans or finding out about them is because of this. I recently bought this iPhone a few months ago, and I think that if my friend actually that, if Lee would know that I have an iPhone now, he would probably wouldn't talk to me. But I anyway found myself getting one of these phones, but of course they came with many restrictions. You know, I had to use it with a specific SIM. I had to in my model I couldn't do videos, if I wanted to get some applications, I had to pay for them, or some applications were just not available in my region, and so and so and so. And of course, I did what many million other people did. I jailbreaked it. You know, I kind of watched all these YouTubes on movies on YouTubes and configured the software. I actually had no idea what I was doing, but in the end, the phone was open, and I could have just use it as I wanted. I could have download whatever, and then suddenly this moment, this total yuppie moment, kind of brought me back to this time, you know, when I was on these trains, you know, because it really, I made the connection that the way that I used that mobile device was really the way that we were using the trains, because we are not supposed to use the trains in that way. You know, we are not supposed to ride them, although they were going there. And I was not supposed to use the phone, but all these functions in it were still there. You know, the manufacturer was just they wanted me to not to be able to use it in that sense. And doing a bit of research, I discovered that this was the way actually one of the techniques that people find out how to use those iPhones to break them, or any other electronic or device, was through reverse engineering. So one of the classic example would be these jerry cans. During the Second World War, I think the Americans were discovering slowly that the Germans have the really great system to transport gasoline from place to place. Of course, they didn't know exactly how it was, but finally they got their hands on one of those jerry cans, and without the plans, they went backwards and manufacture their model. Yeah. And then suddenly, I was again moving forward a bit. I thought about all those moments where people, I mean, when people just need it. I mean, if it's the punks need to jump the trains because they just want to get a cheap, easy ride, and the people that wants to just use their phone in a way that they can use it with different couriers. But then there's all these moments that people just need something really fast, and that's exactly when they really get creative. Let's see if it's no. And I thought I started to look on the internet, you know, and there's like hundreds and hundreds of beautiful moments like that. And it just goes on and on. No, this doesn't work. So I think it's I found it just like in some moment really poetic. Just a moment when people really don't think about the aesthetic, or they have something and they need to change it, and they just work with it, you know. And I mean, it's the carrot in the mattress. Somebody, of course, obviously lost the plug. It's the wide screen. It's the ruler. But for me, it's really just these really poetic moments. You know, it's coming out of this necessity, out of this kind of grabbing whatever that you have to make it work. But I think that's exactly when creativity starts. You know, And this goes on and on. And actually, a few years ago, I started this series that it's called Minor Urban Disaster. It's a series of photos that I do usually while traveling. And it became quite a big thing. I mean, I didn't start it. It started in Flickr by a woman named Cornelia. And there's nowadays, it's really big, and there's many contributors. And I always try to think, like, what brought this moment, you know? And here, obviously, there was some construction going on, and the guy that was doing the construction didn't thought too much on how he put back the tiles. And you see this again, yeah. And this is a really German idea. Or this, but again, I think that these moments really come to you, and then your eyes are just open, and you're searching, and you're looking, and I think that's I really refer to this Minor Urban Disaster series as my sketchbook. Here, somebody, of course, broke in, and the owner of the property, instead of bending back the metal bars, just close it, and you have a beautiful moment. This is actually in Tel Aviv, and but I was shocked in the beginning when I saw that, right? But then I was thinking a bit, what's happening? Does anybody have an idea why this happened? What? It's no, nobody. You have? Maybe you have an idea? No? Okay, it's actually quite simple. It's really simple. Wait, I'm just gonna. I cannot. I have to make it work. Okay, no. Maybe too much gas. So actually, it's a really boring story. I mean, there was a construction site, and there was, of course, the line of the lights that were already there. And the guys were working. Maybe somebody made a small mistake, drove back the truck too far. The light post got bented, you know? And in that point, of course, they have to write to the electricity company that there's a broken light, and somebody needs to come and fix it. But it's all these paperwork, right? They don't want to get in trouble, you know, cutting the lamp or bending it back, you know. So instead of just holding everything, they're just continuing with their schedule. You know, they have the cement car coming next week, so they just work around it, right? And then a week later, I discovered that they trimmed it, you know? But that's probably was being done by the electricity company. So this kind of really absurd moment have a really banal reason. Or here, where obviously they had too long of a fence. Yeah. Oh, yeah. Okay. It worked. Another I'm sorry to wake you up. Sorry. Another of these incredible moments is I found in Berlin. Yeah, and this goes on and on. And if you really want to search for more of these moments, you can just afterwards we can. It's the Minor Urban Disaster on Flickr. This is in Paris. Oh yeah, okay. So last year I was in Japan, and Japan is like the land of the vending machine. You know, they have vending machine in every corner. It's really beautiful. They look good. They smell good. They're really polite. They talk to you back, and they sell you everything you can imagine. They have cold drinks. They have hot drink. It's all in the same machine. They have machines for batteries in all sizes, in all shapes, and going back to the reverse engineering. Oh, now we're really going back to more focusing on my work. Yeah. So going back to the reverse engineering, I had these machines. I was fascinated by them, you know, and I think it took a long time, but finally, when I came to think about it, I thought, what's a vending machine? You know, what's really this drink machine, if not just a fridge, right? A fridge that sells you the drinks, and this is when I built this work. So I think it's really one of the only objects that I can really trace back the process of how I made it. But what I made was a machine, and this is a short instruction. So I just took everything out. I used the empty space of the fridge, opening the door and inserting this. And then one euro. Yeah. And it only works in €1. And you get the drink. So I think... Okay, we're going to open it. It's hard to resist. Yeah. Small detail. Yeah, this was actually meant to be on YouTube, you know. So I wanted some sexual element in the video. So there's going to be a high, you know. It's good.
Yes, it is.
Now I'm going to just really quick show you. It's going to be the inside of the. Oh.
Yeah.
How this work? Yeah. So it's all made from wood. It's really principle. There's the mechanism that holds the cartridge, yeah, and then there's the machine that takes the money, the €1. It's really simple. Money. It's actually really easy to trick it, because anything that is the size of a euro will trigger it, but we're getting better slowly. Yeah, this one. Okay. Yeah. Pull, and you get the drink. Another work was these IKEA pencils. This I actually made a few years ago, but I love free stuff, and you get all these pencils in IKEA, right, for free. And I always leave IKEA with pockets full of these pens. But these fucking pens are too short, right? They're just like they're breaking your hand. And so the obvious idea for me was to put them together, you know, and yeah, again. So of course I wouldn't call that reverse engineering, but some sort of bricolage or. But I think it's like the photos, you know. You walk a lot in the street, and once you see one minor urban disaster, that's it. It's starting, and then you discovered more and more of these moments. So like the vending machine, and transforming it into reverse it into its basic idea, and yeah, so it's just this twist in your mind. The bubble machine. That's yeah. Let's just watch what's going on here. So there's it's a bubble machine. Sorry, but just instead of filling the bubbles with regular oxygen, it fills it up with butan gas, with cooking gas. Yeah, and it's all being driven by the electric screwdriver, and once the bubble drops. Slowly descend, it meets the electric grill, something very similar to those fly traps, these mosquitoes. So it just get a small shock, but in this case a really big shock. But of course, yeah. So for me it was really like this moment when this kind of childhood pleasure of popping a soap bubble become a really the paperwork. Okay, now it's really random. I have no, but I thought that in this moment I will show you as well another work. So this is really relaxing, so you can focus on this, and in the meantime I set up the next experiment. It's again a very simple idea. We have a regular bicycle wheel, and again we have a lighter fluid, so this kind of gas that you use to fill up lighters. And the only thing what I do now is filling up the inside of the tire, the tube, with gas. And does somebody have a lighter? Maybe? No, it's really safe. There's no explosion. Ah, you have. Thank you. Oh. You need to. So this is actually a work that is it's half. It should be the whole bicycle, but I had to bring it, so I just brought the wheel. But the only thing I transformed here was this small jewelry, in a way, that is actually can fit a French ventile and a regular car ventile. Yeah, and I was really for a long time thinking, what would be my what would be my bicycle work, because I always noticed that all the great artists have at least one bicycle work. And I was really, I was like walking around, and I'm like, what will be my transformation? And yeah, and then in the end I just found it. It was without changing anything. You make the viewer completely perceive the object in a completely different way, and this is, I think, a motive that I try to repeat, like. Just a small shift. What else do we have here? Oh yeah. Ooh, okay. We have this is like the premiere of a new invention that's going to revolutionize a lot of things, and it's actually something I made together with a friend of mine, Aram Bartol, a German. Artist, and we're gonna have actually a lot of the object that I do have a do-it-yourself version. So you can. I have a web page. It's called wank.com, but with a double V instead of a W. And so a lot of these things will come or are already there. So for sure this will have a do-it-yourself version. But it's really, you're the first one who see it. Should I? Yeah, I first show it here. Okay. Okay. So we just have yeah, it can turn. Yeah, and you can have it either in negative or positive version. It's up to you. And the idea is that you can really cover a lot of area. You know, with this thing. And we're going to have it much more reliable, you know, but it's so efficient. It's so efficient. This is the negative part. Woohoo! But this is only half of the capacity of what it can do, you know. The best thing is you can do it while you drive, you know. So at this moment, Aram is driving. I'm in the back, and we're just. But of course. Yeah. But of course, you can imagine that you can also print on movable objects. So you can just, all you need to do is stand on the end of the platform, and once the train is leaving the station, you just leave your mark, right, without doing anything. So I think we don't have a really finished name for it, but I'm sure that you will hear about maybe drive-by graffiti, or I don't know. We'll see. Oh, okay. I guess that was it. I have one more idea that I want to share with you, but yeah, the blog, that's Wank. The Flickr, you can find all my photos. It's the Ariel.Chico. And if you're really interested in doing train hopping, yeah, there's a really good zine by Lee, the guy that exposed me to it, and it's called "There's Something About a Train." And I actually searched. You can get still copies out of it. I think he stopped producing it, but there's really wonderful stories. I think the way I told it was really probably boring, because it's really kind of how it works. But there's always, once you're on the train, there's always going to be great adventures and funny moments and really scary moments, and you can go for really many nights going on with these ideas. But the last thing I wanted to show, it's not explosive, and it's really simple idea. I see. Yeah. It's those things. It's also things you get for free in IKEA and in some Baumarkt, so like shops for materials. And it's just a ruler, a paper ruler, right? And there's a bunch of them on the wall. And this also came from a really strong necessity. I was there and I hanging around in the Baumarkt, and there was like this really, like super beautiful girl, like, I don't know, she was looking for cardboards or whatever. And but unfortunately I had no pen, and nothing to write on, no pencil as well. And this idea came where you actually take the paper ruler, and by folding it, you use the number as your card. So you can see here, you can pass it on from 1 to 1, but my number, yeah, 01577. So if you want, you can call me. Okay. But so just go out there, and do your thing without getting scared, and just, okay, that's it. Thank you. Okay. One more. Thank you. Thank you. Thank you. It's okay. That was really quick.
So should I start? Yes. Okay. So I'm afraid my talk is going to be a lot more boring than this. But so I mean, I am a scientist after all, and what I wanted to talk about is since the name of this project is Beyond Entropy, I wanted to talk about entropy I wanted to maybe even try and define entropy, you know, for the people who are not scientists, and in particular, what I want to talk about is the clash between the order in the laws of physics as and the disorder in the world around us, the chaos that we witness all around us. For example, on this table maybe, or on the board, which on the board on which string theorists have been working. So let's see if this works. Okay, so I will first. This should work. Okay. Okay, so I will spend some time talking about the historic things in science and the role that symmetry has played in unifying physical theories, and then the role that symmetry has played in constructing physical theories and unifying them. So by unifying them, this is this idea in physics that people want to describe as many phenomena by as few theories as possible. One example being maybe electricity and magnetism, which were initially thought to be different things, were ultimately described by the same theory. And so symmetry is maybe not the only principle that guides people in looking for physical theories, but it's one of the most important ones, certainly. And it's in clash with entropy, which is entropy is a measure of disorder in the universe, and the fact that things go from an ordered state and then into more disordered states. That chaos increases in the universe, which also gives a meaning to the direction of time, because looking forwards in time, chaos increases. Looking backwards, in the past, there was more order. So there is a clash between the symmetry of the laws of physics and the asymmetry that's present in the concept of entropy. But finally, hopefully, if I get to that point, I will say something about. I mean, there are mysteries that relate to this conflict. We don't really understand why this is the way it is. So let me start historically, and I will not start. So I mean, there were various early theories about the universe, like this one by Kepler, where he thought that the planetary motions were described in terms of these Platonic solids, which so that the orbits of the planets were somehow could be understood as being inside of these Platonic solids, and that these Platonic solids were all embedded one inside the other, as in that picture above. But of course, it's not a theory. First of all, it's true because there are more than 5 planets, and there are only 5 Platonic solids. But more than that, it's a theory that's very different to modern theories. So it describes the planets, but it says nothing about the universe around us. The first modern theory of physics, and that here, by the way, is Atlas holding the heavens. So these are primitive theories from our standpoint, but they are, they were advanced maybe for their time. But anyway, so the first modern theory of physics is by Newton. So you can sort of start. So modern physics starts in 1687 by this very famous book, the Mathematical Principles of Natural Philosophy, the Mathematical Principles of the Natural World. And so what Newton's theory is based on. This is just sort of maybe high school review, right? So it's based on the fact that the stage on which physics happens is a 3-dimensional space, and events in this space are parameterized by time. So time and space are separate ideas, which is something that's that we find intuitively to be the correct thing. And Newton said that objects move in a straight line unless they're acted on by force. So unless they're disturbed, objects move in a straight line. Here, well, you have disturbance by gravity because of the Earth, and some object will move, in a curved way around the Earth. So all that we need in order to describe the physical worlds, given these few basic principles, is we need to know what the forces are that drive the world around us. And then once we know that, we can predict using these equations. We can look backwards in time. We can ask ourselves, if our universe looks like this today, what did it look like ages ago? And so, for example, here, I drew some billiard balls clashing together, right? So the point is that inherent in this Newtonian picture of mechanics is the notion of symmetry. And that's the symmetry not of a particular physical configuration, but of the law itself, which is very different to, say, Kepler's Platonic solids, which was just a symmetry of his idea of what the planets should function like. But this is the symmetry that I'm referring to here is the symmetry of the Newtonian laws, which means that if I have a billiard table here and I run it, for example, back in time, it's a perfectly acceptable physical process. It's just the billiard balls going the other way. If I move this table somewhere else in the room, it's also a perfectly acceptable physical process. It means that the laws of physics are the same here. They're the same where you're sitting. They're the same they're the same elsewhere in the universe, and they're the same also when you translate back and forth in time. So on the other hand, we notice also that there are conserved quantities. So there are things like momentum, like energy, and not like entropy, then is something completely different, which I will come to later in the talk. But say momentum and energy are conserved. The kinetic energy before this collision is the same as after the collision. The momentum before this collision of these two balls is the same as after the collision. And one of the very deep points about physics, not only about Newtonian physics, but also about more advanced theories, was derived by Emily Noether in 1918, so way after Newton's times, which in a very precise manner relates the notion of symmetry and the notion of conserved quantity. So what this very famous theorem says is that for every symmetry, there is a conserved quantity. And in fact, so this symmetry of spatial translations, that the laws look the same whether you move them backwards and forwards, implies that the linear momentum is conserved. The symmetry of the laws of physics under rotation implies that a quantity called angular momentum is conserved. And the symmetry under time translations implies that energy is conserved. That's probably one of the most important quantities in physics. This is just some drawing of what angular momentum is. It's not too important because maybe people are more used to momentum and energy, but angular momentum is something. I need to replay that maybe. Well, angular momentum says that the object will trace out equal areas in equal times. So it will move more slowly if it's further away, more quickly if it's nearer to the object it's revolving around. And it's something that it's actually something that Kepler found out, but not by Newton's equations of motion, but only by simply observing what's happening in the heavens. So the question then is, well, I haven't told you yet anything about the fundamental forces. The question is, what are the fundamental forces which govern the universe? So one of them is certainly gravity, and the force is determined in terms of the masses of the objects involved. And another example of a force is the electric force between charged objects. As you can see, these formulas look very much the same. I'm only, don't be too afraid of the formulas. I'm only writing them for fun, so to say. But just because, sometimes they illustrate, even if you don't understand what they mean, they illustrate what quantities are involved in determining the forces. So the quantities involved in determining the gravitational force are the masses, and the quantities involved in determining the force between charged objects are the charges of the objects. The difference is that these charges can be positive and negative, so the force between charges can be either repulsive or attractive. So then using these forces and Newton's equation, force equals mass times acceleration, we can predict everything that happens, to gravitational particles, any number of them, and we can be very clever about many things. This is the first example of unification and where new things start happening after Newton. So this is due to Maxwell. It's the time when this was derived is around 1865. So we have the law for electricity, which is same as the law for the force between charges on the previous page, and this is the law for magnetism, for the force in a magnetic field and the force in the electric field. And the electric and magnetic fields were thought to be separate things, so there was a separate theory for electricity and magnetism, until Maxwell wrote down his equations, which, as you see, even though I don't, I expect anybody to try and understand this, you can see that they involve the electric field and the magnetic field in the same equation. So it means that these theories are merged together. They're unified. And furthermore, what's even more weird, and what took people 40 years to figure out, is that the presence of the speed of light in the equations. Because you see, electricity and magnetism, they sort of talk to each other through these equations, and they propagate each other. So say an electric impulse will push a magnetic impulse forward and so on, and the whole thing will move at the speed of light, and the whole thing will actually be light. The whole thing, that's how, that is what the correct description of light is. Now the strange thing about these equations is that this speed appears as a constant, which is where Einstein comes in, right? So our intuition would tell us that if, say, there's a ray of light traveling so we're standing here, right? And we're watching a ray of light propagating in this direction. So it propagates at the speed of light, c. And then there is a spaceship traveling at the speed v, also in the direction of the light. Then you would expect that this spaceship sees the light moving at a slower speed. You see, in the same sense that as when you're in a train and you see another train next to you and you're both moving, the other train looks stationary to you, you see. But if somebody's standing on the platform, both of the trains are moving. So this is a perfectly, I hope, by the way, don't feel free to ask me questions if I'm confusing you too much with stuff. So you would expect that this spaceship here sees the speed of light not as c, but as c minus v. So how can it be that in Maxwell's equations there's only one constant speed of light? So people were wondering about this for 40 years until Einstein just said, well, that's the way it is. The speed of light, everybody measures the same speed of light. And furthermore, what this means is that time and space cannot be separated. If you remember the picture of Newtonian physics, you have the three-dimensional world, and at every point in time, you have a copy of the three-dimensional world, and you have time parametrizing events. Well, let me put it a different way. You have time as a separate parameter giving you, parametrizing events. I don't know how to explain it better. Time is not a geometric dimension, in other words. It's simply a parameter. It's simply a number, which gives meaning to something being before, something being after, and so on. What Einstein says is that this is actually completely wrong. So you have to understand time geometrically as a part of a four-dimensional world. You see, here at every point in time you have a copy of the world with a certain event. Here you have the same copy of the three-dimensional universe where this particle has moved along, and so on. This whole thing, in a sense, even in a Newtonian sense, has four dimensions. But time is, in a sense, separate. What Einstein said is, you need to incorporate time as a fourth dimension in a very, very, peculiar way. So you have to think of this four-dimensional space, which includes three dimensions of space and one dimension of time, as having a very strange notion of distance. Normally, we're used to measuring distance, like I say. The distance between me and you is something positive. It's 2 or 3 meters, right? In this world of Einstein's special relativity, the distance between two different points can be positive, can be 0, or can even be imaginary. So the distance squared can be either positive, 0, or negative. So if you take the square root of a negative number, then you're working in complex numbers. These, if you remember maybe from, I don't know, somewhere in your lives that there are these things that square to -1. So what is the meaning of this? The meaning is roughly as follows. If there's, it takes the light, say, 8 minutes to reach me from the sun. So there's an event where the light was emitted 8 minutes ago at the sun, and there's an event where I see the light after 8 minutes here. In this sense of special relativity, the distance between me here, now, and between the light at the sun 8 minutes ago is 0. So anything that can be connected with a light ray, the distance between any two events which can be connected with a light ray is 0. And this corresponds in this picture to this light cone, you see. So this, if this is the observer, then the light cone describes all the events which can be connected to him by sending a ray of light. Anything inside this cone can be connected to him by sending a signal which is slower than the speed of light. So he can sort of communicate with everything inside this light cone. Now, on the other hand, there's no way for me to communicate with the sun right now, because to do that, I would have to send something, a signal that instantaneously makes it to the sun. And we know that the highest speed that one can reach is the speed of light. So that's impossible. So all the events that we cannot reach are outside of this light cone. So we have this strange four-dimensional geometry with this strange notion of distance. And this very simple geometric and very symmetric idea gives rise to all the weird things that people hear about relativity, like that energy is equal to mass times the speed of light squared, that energy and mass are the same thing, in other words, or this fact that moving clocks run slow. So that, you know, if you're trying to look at a clock inside a spaceship, it will run more slowly than for the person inside that spaceship. All kinds of weird things are possible in relativity, but they all come down to this simple symmetric geometric idea. Well, relatively simple. It's weird, but it's not complicated, you know. Now, the next big theory, also due to Einstein, is general relativity. So here, the idea was to say, well, the world has this geometry with this strange notion of distance in small regions around, say, me. In a small region, special relativity is valid, but globally, space and this four-dimensional space-time manifold is curved, and gravity is not described by a force, but it's described by the curvature of space-time. Like you see in this video, the planet is orbiting the sun, say, in the middle, and the sun curves the space-time. So as far as this planet is concerned, it's just moving in a straight line. It's just moving. The fact that it's going in the circle is due to the curvature of space. And the other thing that this video demonstrates is that the signals travel at the speed of light. So if somebody removed the sun, as happens in this video, the time for the planet to feel that the sun isn't there isn't instantaneous like it would be in Newton's theories, but it takes 8 minutes for this effect to reach the planet. It's like a gravitational wave, you know, that travels along, and then after 8 minutes, our planet here notices that the sun isn't there anymore. So this is the idea of general relativity, that gravity, we do away with gravity by using the curvature of space-time. I'll keep using this. But, this is not something really that's, this idea of doing away with gravity is not something that's really intrinsic to Einstein as such, to special relativity. You can also imagine it in a very, in a sense in which, in a much more intuitive sense, right? Just from the fact that, I mean, people are familiar that, you know, if you're in free fall, you know, if you've jumped off of something, or if you're in these experiments, you know, where the astronauts are taken before they go into outer space, where the airplane plunges down into free fall, and they can't feel gravity, they're just floating around. So if you're in free fall, you don't feel the force of gravity. The underlying reason for that is going back to those old, those equations of gravity well, maybe I can, I don't know if I need to say that, but maybe I will. If we go back to this equation that describes the force of gravity, you see it involves, the force of gravity involves the mass of the object, but the mass of the object also enters the equation force equals mass times acceleration. And this is the underlying reason why you can do away with gravity. You cannot do away electromagnetism in this sense because the force is proportional to the charges, but the acceleration is proportional to the masses. And they're not the same. So, but in any event, suppose that you are then in a freely falling lift. You're standing inside a lift, and what this principle of equivalence, as it's called, tells you is that you cannot tell that you're being accelerated. Everything inside looks. You look like there's no force. You don't feel any forces acting on you. You can put it that way. So you're in a freely falling lift, but you can feel gravity in the following way. If you're in a freely falling lift like this, and you have two balls, say, you let go of them, and they will just, because you're in free fall, they will just sort of, stand there, like as if you're in a spaceship. However, after a while, you will see that they come closer together, and the reason is because you're falling towards the center of the Earth, and both of these balls are falling towards the center of the Earth, right? So in your frame, they will slowly start coming together. Does that make any sense at all? Or roughly, anyway. Yeah, I mean, because everything has to converge. Once you get to the center of the Earth, everything has to come together, including yourself and the two balls. So in your frame, they're coming closer and closer together. On the other hand, if you put one ball higher than the other, there's a different effect. The ball here will feel more force because it's closer to the Earth than the ball up here. Slightly more, but nevertheless, it will be accelerated a little bit faster than the one up here, and you will see the two balls coming apart in this direction. So you have balls coming together like this and moving apart like this. These are tidal forces. And they are actually, in a real sense, what you mean by the curvature of space-time, by the fact that the space is curved. In a very small region, you cannot tell that it's curved. But if you look at things like this, then you can tell that space and time are curved. So what have we, just as a very rough analogy, what kind of transformations have our physical theories undergone up to Einstein? We start with Newtonian mechanics, where the stage for physical theories is a three-dimensional world. Events are parameterized by time. It's the most intuitive theory of all. However, then special relativity tells us, well, that's not quite true. You need to combine time and space. There's the speed of light. So the stage gets slightly skewed using this weird geometry where distances can be zero and imaginary and this kind of thing. And then on top of that, general relativity curves the stage. Now you can put any kinds of plays. I mean, one point that I'm trying to make is you can put any kind, as far as the mathematics is concerned, you can put any kind of play on the stage. You can come up with theories which have nothing to do with the real world. And that's perfectly fine, right? But it becomes more and more difficult. The further down you go, further down you go this line. The further down that you go down. Well, in Newtonian mechanics, you can come up with any kind of theory, and it becomes more and more difficult to do so, say, in general relativity. And of course, one other weird thing has happened at this stage. That gravity is not a part. Gravity is not to be understood as a theory that happens on the stage. It's part of the stage itself. Other things, like you can put electromagnetism on top of general relativity and all kinds of other things. But it's gravity. Gravity itself is mixed in together with the stage itself, which is a very weird concept. But this is only half this weird story. What's a lot more weird and mysterious is quantum mechanics, which deforms these stages in a much more radical way. And quantum mechanics, is very, very counterintuitive. But you can understand things roughly in this way by considering this experiment. So you have, you're shooting a gun through two slits, right? So supposing that you shoot the gun just through one slit and close the other slit here. You can imagine that the bullets sort of ricochet in different directions. They're most likely to go forwards, but they can also, hit the screen at different angles. And this sort of describes the probability of the bullets hitting the screen. So it's most likely the bullet will hit the screen going straight through the hole and straight on, but it can also hit it on either side. And then if you have two slits, you combine the probabilities, and what happens is that the gun hits the screen mostly in the middle, and it's less likely to hit the screen. The bullets are most likely to hit the screen in the middle, and less likely to hit the screen on either side. Now you can perform the similar experiment using waves, here a laser, but here a slightly different thing happens, is because the waves can combine, in a more complicated manner. So as you've maybe, as you can sort of imagine waves moving through a pond or something, if they go through two slits and when two circular parts combine, they combine in a rather complicated way. And what happens is that you see a pattern like this on the screen, very different to the thing you saw from the bullets. Now the question is, do things in the real world behave like particles, or do they behave like waves? Light, say, behaves like a particle intuitively. Electrons and things like this, atoms behave more like particles. But the answer that quantum mechanics proposes is that everything, absolutely everything, behaves both like a particle and like a wave. So it's stated more accurately, things evolve like waves, but are detected like particles. So light in this picture evolves like a wave, but you only ever measure a photon. You only ever measure a certain amount of energy. You can't measure an arbitrarily small amount of light. It comes in lumps. It's measured as a particle. Same, the bullets are much larger, but they're obviously measured like particles, but they also behave like waves. So the fact that you see this pattern like you see on the screen is just due to the fact that the bullets are very large. You see, if you move these two slits very far away, or if you made the light very, if you forced the light to have a very short wavelength, you would see the same kind of pattern as with the bullets. So the wave determines the probability of detecting the particle. So the whole world, the interpretation, the physical theory is interpreted in a probabilistic way. In Schrödinger's famous experiment, using this kind of maybe, laser or something like this, he puts a cat, there's a cat in a box, right? And he has a gun, which fires depending on the outcome of a quantum experiment, which then puts a cat in, because we haven't measured what actually happened, the cat, the point is that until you measure, things evolve in this strange quantum mechanical way as waves. It's only when you measure it that you know whether something is there or isn't there. Whether, if you can look at this screen, and until you've measured the particle, you only know that you will measure it with a certain probability, but you don't know whether you will measure this particle for certain. So here, this cat has been killed by a quantum effect. So until you actually look at the cat, you will not know whether it's alive or dead. So the cat is in a box, and it's been shot at by some gun, which was triggered using some quantum experiment, using lasers or something like this. And until you open the box, the cat is in a superposition of being alive and dead, and it keeps evolving according to the laws of quantum mechanics until we open the box, when it happens that we notice that the cat is either alive or dead, with the probability of determined by quantum mechanics, depending on the setup of the quantum experiment. So this is a very, very weird thing, which deforms our stages in a very radical way. So Newtonian mechanics is made, so there's a set prescription for turning Newtonian mechanics into quantum Newtonian mechanics, if you want. And there is a similar, relatively well understood procedure of turning special relativity into quantum special relativity. But it's very difficult. This step is already very difficult. There's sort of a conflict between quantum mechanics and special relativity. And general relativity, nobody really knows how to quantize this general relativity. And that's one of the big outstanding mysteries in science. And it's where string theory string theory seems to provide a way of understanding quantum general relativity, but it's still very, very poorly understood. You can sort of see why it's problematic, because, by looking again at an equation, which you don't have to understand, other than to notice the fact this is Schrödinger's equation, which describes this wavy evolution of quantum mechanics, and what's weird about it is that time enters in an asymmetrical way. You see, I told you, in special relativity that time and space should be sort of understood as different, in a mixed up way, as different facets of the same thing. And here, time enters asymmetrically. So you can just about get it to work with special relativity, but with general relativity, where space is curved, things blow up, you get infinities, and you don't know really what's going on. I will skip this part because it will take too long. So here I was just going to talk about so I've talked about electromagnetism, right? And there are various other nuclear forces which also get combined by considering more elaborate symmetry principles. But maybe leave that for a different talk. So string theory. What is the idea of string theory? The motivation for string theory is precisely to resolve this problem of combining quantum mechanics and general relativity. The idea sounds maybe a little bit primitive even, that in all these theories of, say, electromagnetism or something like this, the particles are described as points, as mathematical points. In string theory, we try and the idea is to describe particles not as points, but as little, very, very tiny strings which vibrate. These particles here are sort of the known physical particles which are being measured at, various properties of these particles are being measured at CERN and things like this, right? So there's a bunch of them. And one thing that I will say about them, there are two kinds of particles, you see. There are particles that carry force, and there are particles that are what we consider matter. And the difference between them is that the particles, the matter particles, you cannot bring them, if you try and bring them close together, they will move apart. They will be forced apart by quantum effects. Whereas these particles that carry the forces, that carry the photon carries the electromagnetic force, these carry these nuclear forces. But in any case, these force-carrying particles can be brought very close together. They can be, if you want, at the same place at the same time, This is not true for the matter particles. But in any case, string theory is able to describe these particles as different vibrations of the string. So it's again an idea of unification, even though it's maybe less driven by symmetry, because we're just trying to combine general relativity and quantum mechanics. But so it's more driven by the idea of unification. So there are open strings and there are closed strings, and they vibrate in different ways. But it doesn't quite work as nicely as it looks to start with, because for one thing, this superstring theory implies two very important things that we don't immediately notice in the real world. One is supersymmetry, which is that it says that there's a symmetry between the force-carrying particles and the particles, the matter particles, which is not something that we observe. And the second thing is that we can get general relativity to work. In fact, string theory requires general relativity. It doesn't work without general relativity. But it's general relativity in 10 dimensions, not in 4 dimensions. So there are all kinds of, it's quite a weird thing, saying that the universe is 10-dimensional and not 4-dimensional. So how do we get to the real world? Well, we try and construct solutions to string theory where at every point in our universe, there is an internal space of 6 dimensions, you see. So we have 4 big dimensions and 6 small dimensions at every point, which we cannot notice because they're so small. But altogether, it gives us the 10 dimensions of string theory, which is then, which makes the, which is what we need for string theory to work. Now these spaces are called Calabi-Yau manifolds. So if we want to try and describe the real world using string theory, then at every point there is something well, here it's a 6-dimensional space. Obviously, you can't draw 6 dimensions, on a screen, but it's a representation of the 6-dimensionals. It's a projection of the 6-dimensional manifold. And then we can get something, we can get all kinds of theories resembling the real world. The problem is that there are too many. There are so many such manifolds which give us acceptable physical theories in 4 dimensions that we don't know really what to do. There are, in fact, 10 to the 500 such candidates. So string theory is, in a sense, it's an embarrassment of riches. There is too much stuff going on, and there is a lot more that I haven't even mentioned. There are not only are there strings that happen to exist just by. It's more well. Why did I put Alice coming through the looking glass? Is because you consider this simple idea of particles being strings rather than points, and you come into the huge world where. Which is consistent and which is in a sense unique, but there's so much going on that you don't really understand what is going on anymore. So when you just consider this, you get into this world of string theory, then you find that there are D-branes. There's objects which are not just, so you don't only have strings, you also have 2-dimensional membranes. 2-dimensional membranes. You have membranes of higher dimension. All of these objects exist in string theory. And furthermore, there is an 11-dimensional theory which is even less well understood than string theory, which seems to be sort of the mother theory of. Well, okay, maybe I'll say a few words about this just quickly. So, there are various types of string theories that people have discovered. There were 4 or 5. So people ask, why isn't there just one string theory? Why are there 4 or 5 string theories? And it turned out that they're all related, really. They're all different faces of the same theory. And not only that, but there is also another theory, which is 11-dimensional, which is not based on strings, but on something that's not well understood. But people believe that it should be there, which in a sense, which is needed to combine the different string theories together. So there is a lot going on, but it's not very conclusive. Now, coming to entropy. Entropy is something completely different than anything I've talked about yet, really. So I said that laws are symmetric with respect to time. So people are very willing to accept this picture here of a tomato getting destroyed by a bullet coming through it. It's a physically sensible thing which happens. It's an increase of this order. We had a tomato, and after the bullet hit it, we have a whole mess of things which doesn't resemble the tomato at all. Now, the opposite thing is extremely weird, no? Nobody expects to see a tomato spontaneously coming back together and emitting a bullet. That doesn't happen. So there is obviously some kind of a conflict between what I've said. I've said that the laws of the universe are symmetric with respect to time, but yet this kind of asymmetric thing, running things back in time here, doesn't happen. Even though this is a perfectly acceptable thing as far as the physical laws are concerned. So where is the catch? First of all, let me just try and say what entropy is, which maybe is. Well, I thought I'd do that. Entropy is a very subtle concept, but maybe I thought it would be a good idea because this project is called Beyond Entropy. So it's a statistical quantity. That's the first thing that one can say about it. It's like temperature. So temperature measures the average kinetic energy of a particle per degree of freedom. It doesn't matter what that means. It just means it measures the average. It measures the average kinetic energy of a particle. So it's not, in a sense, a fundamental quantity because there's somebody looked at various particles, right? In principle, and calculated the average of them, and that's the temperature. So what I'm trying to say is that it's more fundamental to know the information about every particle rather than to know the average, if you're looking to do fundamental physics. Now, entropy is the measure of disorder. So what do we mean by that? An alternative definition is that it measures our incompleteness of the incompleteness of our knowledge about the system that we're considering. This is the equation for entropy. And Pi is the probability of the system being in the state I, right? So forgive me for writing down the equation, but it exhibits well, there's one obvious thing that it exhibits. If you remember what the logarithm is, the logarithm is, well, it involves a base, so say it has base 2. So it's the number to which we need to take 2 in order to get Pi, right? So if Pi is 1, the power to which you have to take 2 to get 1 is 0. Now, if Pi is 1, it means that there's no probabilities involved. We know everything about the system. We have a single probability which tells us the system is in this state. In this case, the entropy is 0. So if we know everything about the system, the entropy is 0. Because the logarithm of 1 is 0. Entropy is maximized when our knowledge of the system is minimized. So what does this mean? Suppose our system is a bunch of coins, which, say it's some M coins, which can either be heads, heads, tails, 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 heads, 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 or they can be in any other configuration, right? It can be any combination of heads, tails, and so on, right? It turns out that there are 2 to the power of M different configurations. And if we don't know anything about the configurations, so we would just say every configuration is equally likely. So every configuration is 1 over 2M, 1 over 2 to the power of M. Now, if we plug that into the equation for entropy, then we see that the entropy is proportional to the size of the system, to the number of, for example, dice in this case. So to summarize, if we have all the information about the system, if we have some probability 1 that say the system is heads, heads, tails, 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 heads, 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 and the probability of everything else is 0, then probability entropy is 0. If we have no information, we say everything is equally likely, then the entropy is M and it's maximized. Okay, so now this is perhaps perhaps going too far in trying to describe this, but it's sort of it should enable me to give a really proper definition of entropy and tell you what's going on with this asymmetry with respect to time. So to understand entropy for a real system, not for a system of dice, which is not a real physical theory, we need to consider phase space. Now, phase space is the space of all possible states of a system, similar to the space of dice. The space of all possible states of dice is the space of all possible combinations: heads, 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 everything heads, heads, tails. all the combinations you can come up with. All these different states enumerate, all these different possibilities enumerate the different states. So for a real, say, particle, the state of a particle is determined by its position and by its momentum. So it's 2 numbers that determine, well, in 3 dimensions, it's 3 numbers that determine the position and another 3 numbers that determine the momentum, the direction of the particle in which the particle is moving. So this then, we need these 6 numbers to describe a single particle. For n particles, we need 6 to the n coordinates. So phase space for a complicated system is very, very large. It's humongous, for any, if you're considering, say, if n is the number of atoms or something like this. Now, if we do not have full information about a system, then we need to pick a volume in phase space. So we know that our particle is somewhere in this volume in phase space, but we don't know exactly where it is. And entropy is the logarithm of the volume of the phase space. So yes, well, that's what happens if you take the analog of these dice into the real world. Is the volume of the phase space. It's the logarithm of the volume of the phase space. Now, the point about the logarithm, which I should mention, is that it's an increasing function. So if the volume increases, the logarithm of the volume increases. Much more slowly, but it increases. So the entropy increases if the volume of the phase space increases. Now, where does this asymmetry come from? The asymmetry happens because the symmetry of the physical laws is reflected in what's called Liouville's theorem. And it says that if you start with some volume in phase space and it evolves in time. Note, it moves to some different volume in phase space. The volume itself, it can change shape, but it will, the volume will remain constant. So it's this conservation of volume that reflects the symmetry of the laws of physics. Yeah, so dynamical evolution does not change the volume of a blob in phase space. However, what happens in the real world? See, what can happen is that you start with some volume here, and as it evolves, the volume doesn't change, but it spreads around. You see, it spreads like a big octopus. So you can imagine, for example, some cotton wool or something filling up this whole room, you know. Most of it is empty air, right? It still fills up the whole room, and if you compress it, the volume is going to be very small, but it will have spread out everywhere, you know. And this also, the reason why this happens is chaos. So what does chaos mean in terms of these phase spaces, right? So it means that if you start with two different points here, they will evolve as the theory moves on. They will evolve to points which are, if you start with 2 points close together, they will move very far apart. If you consider a point just very near to this one, but not exactly at this point, right? It's just somewhere very near. If you follow this back in time, it will be somewhere completely different than the point here, you see. So it just means that a slight change in the initial conditions, you know, a butterfly flapping its wings or something like this, will change the outcome of what happens drastically. And this is the reason for this spreading of the phase space. Now, I said that the entropy is the log of this volume. So if the volume doesn't change, the entropy doesn't change. So the second law of thermodynamics says the entropy always increases. And I've just told you that the volume never increases, that the entropy never increases. So what's going on? The entropy increases only if you introduce a coarse graining. It's called the coarse graining. It means that you cannot, and it's physically a very plausible thing to say. It means that you can never determine with full precision where something is in phase space. Everything is an approximation. And if you consider this approximation, as the blob spreads out, you see, you cannot, these are all very, very thin volumes, but they're approximated by blobs. And these blobs will connect the different tentacles. And when they connect the different tentacles, the volume will actually increase. So if you're able to understand every particle, the position and the momentum of every particle in the universe to an incredible precision, to the full precision, then the second law of thermodynamics is not true. The entropy remains the same. But as soon as you make any small approximation and you wait long enough, the volume will increase. So if you're God and you can follow everything in the universe, for you the entropy never increases. If you're a human being, then entropy increases. So it's a very subtle concept, but this is what happens. This is the definition of entropy. It depends on the coarse graining, and it depends on our. So obviously, as the volume increases, we actually lose information about the system. Here is just a brief. Well, the growth of this volume is described by fractals. So, and fractals are very simply described. They're objects which are very complicated, but they're described by very simple rules. Just like our physical theory is very, very simple, or can be very, very simple, but the evolution is extremely complicated. And I'm getting there. So, furthermore, this is another way to understand the connection with information and between information and entropy, because essentially entropy and information are the same thing. So just another example of the second law. The second law tells us that if we put two objects, one cold and one hot, together, and we wait long enough, they will both cool down. Well, they will both come to some temperature in between. They will both come to some warm temperature in between. But what will never happen is that we have two objects at the same temperature, and they spontaneously go into a state where one is cold and one is hot, right? So that's intuitively, that's what the second law says, right? Now consider this is an experiment devised by Maxwell, which tries to describe this happening. So you have you have two boxes together right here, and you have molecules moving quickly and molecules moving more slowly, which is what happens in any thermal system. They all move, the average speed is determined by the temperature, but some move more quickly, some move more slowly. And the temperature is the same here and here. So these black ones are the faster ones, the white ones are the slow ones. And then you have a demon, and there's a flap between these two compartments. And the demon is looking at the molecules. And when he sees a fast one coming this way, he lets it into this other chamber, you see. And when he sees a slow one coming, he lets it come into this chamber. So, and after a while, he has moved all the fast molecules into one chamber and all the slow molecules into the other chamber. So he has done effectively this. He started with an object where two things are warm. He made one cold and one hot. So where is the paradox here? Now, for a long time, people thought, well, when this demon is measuring things, he must be increasing the entropy there, right? But this was only resolved. You see, some of these things take ages to resolve. I mean, these are quite difficult ideas, some of these. I mean, this was resolved in the early 80s or something, and Maxwell came up with this theory in 1860 something, right? What happens is that the demon needs to put the information about the molecules into memory, into his memory. And the memory, so as long as he has enough memory, he can keep doing this. It's when he runs out of memory, when he decides that he needs to erase something to record something else, that's when he increases the entropy of the universe. So the second law still holds, but in a very, very subtle way, so to say, right? And the other thing that you can notice is these two things, this configuration and this configuration have the same energy, right? It's still the same number of molecules moving at the same speeds. But you can see that you can use this one to do some useful work because you have fast-moving molecules here, slow-moving molecules here. So there will be some pressure going this way. So you can put a piston there or something, and let the system do some work. Whereas here, you cannot. I mean, if you put a piston, it will just sort of wobble about, but it won't do any useful work. So here you can also see that there's another alternative definition of entropy, that it's the amount of thermal energy which allows you to do useful work. So the question is obviously the Earth and everything that we see around us is not in thermal equilibrium. We're able to do useful work all the time, or less useful work. So how come the universe isn't in thermal equilibrium? If it's been around for so long, and if the second law is true. And furthermore, this is a slightly different point. You see, people think that we use up energy on the Earth doing things. This is not actually true. The Earth gets its energy from the sun, at least most of it. And it radiates, it so happens that it radiates the same amount back. So it gets, during the day it's heated, during the night it radiates. The net change in the energy that we have around is zero. What does happen is that the sun decreases the entropy on the Earth, you see. So the photons that come in are of low entropy, and the photons that leave are of high entropy. So that's how we do work. We don't do work by using energy, we do work by using entropy. And so the question is, where does the lowness of the entropy of the sun come from? And you can trace this idea back. Then you look at the sun, you go back to the Big Bang, and the point is that you can trace this lowness of entropy all the way back to the Big Bang. The Big Bang had to be a very, very special, thing with an enormously low entropy, in order for us to be here doing what we're doing, and for us to observe the universe the way that we see it. So here is an illustration again of this phase space. So the question is, how unlikely is the Big Bang? So this is the phase space of our universe, and we are, say, somewhere here now. So we're not in thermal equilibrium, but we are slowly moving towards thermal equilibrium. You see, and it will happen maybe in 5 billion years. We'll be in thermal equilibrium. But what is the likelihood if somebody just threw in a propagation through the phase space? What is the likelihood that it will have started in something as special as the Big Bang? And this is like one of the biggest numbers you've ever seen, you'll ever see in physics. The probability is incredibly, incredibly low. It's 10 to the power of 10 to the power of 120. It's an inconceivably humongous number. And there's no good explanation for this. So the question is, have we resolved the mystery of the time reversal? Well, apparently we have. It comes from our ignorance about the universe. But maybe this is not quite true. We have certainly not resolved this point about the Big Bang, why the Big Bang is so special. Another thing we haven't resolved, well, the coarse graining is a fundamental procedure, but it could be, of course, that, I mean, physics doesn't tell us really anything about the consciousness, you know, what the conscious observer is. So if maybe in the future physics will be able to say something about consciousness, maybe this lack of information will be a fundamental quantity, you see. So somehow this, yeah, I mean, one could imagine that the entropy and the lack of information will be something very fundamental to consciousness. But that's, you know, nobody's even attempting to think about this, you know, because it's too difficult. And the other thing is quantum mechanics. I haven't mentioned too much about quantum mechanics, but it is the only, well, it's the only other place in physics where something irreversible happens, where you can't run things back in time. And how does this happen? Well, I told you that, for example, the cat involves in this superposition of being alive and being dead until you measure it. So this evolves according to the rules of quantum mechanics. But the measurement itself doesn't evolve according to the real rules of quantum mechanics. You either, after the measurement, the state is reduced to one of the two possibilities. And this then again evolves according to the rules of quantum mechanics, but this reduction does not. One way to understand this reduction is again to say, well, there is an environment out there which we don't understand, and the interaction with this environment causes this reduction of the quantum mechanical wave function. But this is also, again, it's unsatisfactory in the same way. What is the fundamental status of this lack of information about the environment? Is it something, you know, should this have a fundamental, should this be a fundamental part of our theory? And then the further, an even more difficult question is, does quantum gravity play a role? And I mean, nobody understands quantum gravity really. Some people think that it might change the nature of quantum mechanics. You know, that it might explain this measurement, this reduction of the wave function in some more satisfactory way that doesn't involve this business with the environment. But it's not clear what happens, you know. It's not clear what happens at all. So there are, so it's not, the answer is, and the conclusion of this talk is that it's far from clear whether the second law of thermodynamics should be considered fundamental or not, and whether entropy should be considered fundamental or not. So it's not clear what's beyond entropy. Yes, that's all.